Hi, hi to all. Uh, this is one video that I had suggested that we will be having one online seminar, but as online seminar could not be arranged, I am giving a self-instruction video on the topic of effective section modifiers, that is crack sections for seismic analysis and design of the RC building structures as per IS 1893 2016. The subject has been taken specifically because many people still have doubt how to analyze and design the building structures using the section properties. Now, at what place to give this section modifiers, and our IS 1893 2016 says about the analysis. Should it be part of the design or not? So, to follow that, I would suggest I am following the ACI 318 norm. Also, the same has been mentioned in IS 16700. The same can be applied to all the buildings that we are doing the procedure for the section modifiers. The reason specifically the modifier came in 1893 is that the tall buildings are governed by wind. However, the low-rise buildings are always governed by earthquake, and hence the other forces are not been mentioned. However, this criteria of the crack section is valid for all load cases that may lead to collapse of the structure. So in the governing criteria, which may be gravity, because before failure the structure will crack, and under nonlinear action the structure will crack. So as the load deformation curve shifts from the yield to the plastic zone, okay, then your cracks will form, and those cracks will open and close during earthquake due to cyclic action. In other actions it may open and it may not open and close, but due to cyclic nature of the earthquake the cracks will open, and then it will close, and after the earthquake the building will be able to take the gravity load. So this is the idea behind considering the crack sections, that is the stiffness of the members reduce after crack. So that happens only in the ultimate load case. So there are two criteria. One is ultimate load case and one is serviceability load case. Previously, when this had newly come, it was understood that serviceability conditions means the wind case, and ultimate means the earthquake case. However, that is not the criteria. The criteria is the crack sections happen in all cases where the failure comes, and the failure comes in the ultimate load cases. So ultimate load cases has load factors in them. So whatever are the ultimate load cases related to load factors, for all those cases you have to consider the crack section modifiers for analysis as well as the design. In the analysis part, when we are considering the wind, uh, in that case it is a elastic analysis, and hence we are saying that it should not become part of the wind load case, and hence only the seismic load cases should have the section modifiers in analysis, and unscaled response spectrum should be used to get the highest displacement for the ultimate load case. So for the serviceability load case as well. So whatever the load cases you are using in the design, you are using in the analysis, the same has to be used for that same model has to be used for the design. So considering that the failure load may be wind, failure load may be earthquake, failure load may be due to gravity as well. So what all load case can lead to failure, and in that particular scenario we have to consider a model that is relevant for all load cases, not just for the earthquake load case. So this short instruction video, I am not going through the modeling because you know that how to apply the modifiers, but when to use the modifiers is critical, and whenever we are doing with the Going ahead with the modeling of the structure, the section properties relevant for the ultimate load case with load factors should have the modifiers. Serviceability load cases does not require modifiers. However, for earthquake action in the analysis unscaled response spectrum, you have to give the modifiers. So the same modifiers given in the ECI 318 can be used to understand and then apply it in IS 1893 2016. Okay, so understanding purpose, you should understand what is there in ACA 318. The same understanding you can apply when you are doing for the other codes in India. And let me share the one document that I had prepared. I hope my screen is visible to all. And what basically is crack section properties and what do they indicate? Seismic analysis and design of reinforced concrete structures are performed based on linear response. However, it is universally known that the earthquakes consider the inelastic response and cracking is accepted due to that response reduction factor of 4 or 5 or 3 that we are taking. So the structure has to get cracked in the inelastic response during the earthquake in real condition. Therefore, element property should reflect this condition and inertia of beams and columns should be reduced accordingly. So that is the idea in linear analysis. Also, we should consider the cracks will happen and moment of inertia will reduce for the structural elements, beam, columns, walls. All elements would behave in that particular manner. That simulation in your model will help you to actually get benefit in terms of the forces will reduce as the time period will reduce and your displacement whatever is going to happen in your structure you will be able to control that. Deformations shall be reliably quantified for which relevant section properties are important for estimation of the lateral drifts. So earthquake is more deformation control action and hence this reduction in properties will help you estimate those drift demands, and based on that you can check your design whether it is satisfying the interstory drift as per the IS code or not. That is 0.4% for buildings with masonry. In 2008, Nigel Priestley said that if the serviceability criteria are to be satisfied with a reasonable degree of confidence, the extent and influence of cracking in members and the contribution of concrete and masonry in tension must be considered. So if we want to have more confidence on serviceability criteria, how much cracking is happening and how much tension force is generated in the concrete, if it is estimated properly, you will be able to get a better clarity on the serviceability conditions. In 2003, Nigel Priestley computed elastic periods are probably wrong, and moreover, the force distribution throughout the structure, which depends on the relative stiffness of the elements, may be excessively mistaken. So, what if we are considering the uncracked properties, then your load distribution as well as the behavior of the structure is not captured for the real condition of the earthquake, and hence it is necessary to consider the section modifiers that are in the correct section properties for the beam columns and walls. The flexural cracking varies along the element length, therefore moment of inertia I also varies along the element length. So as the cracking is different at the center and the end portion, you will find that I is not a constant term in one element, whether beam or a column or a wall. Now you cannot estimate I for each and every length of the member, and hence it is suggested that uh, we should take the reasonable average value for this cracking in the elements, and that's why you are seeing that only one value of zero point 0.7 in columns, 0.35 or 0.25 in beams, and these slabs has been taken, and for wall also similar values has been suggested. So that is a single value is given. However, for each unit length, if you measure, the I will keep on changing along the length based on the bending moment, axial force, reinforcement, and geometry of the element. So to make it this procedure more practical, it is suggested to use one single average value, which we are using for modeling the crack in the elements. So from there, in 1992, in 1992, Pauli and Priestley gave the effective moment of inertia values for rectangular beams as zero point 0.3 to zero point 0.5 of I gross. For the recommended is zero point 0.4 of the I gross for beams. I and L beams, it is 0.35 of I of gross. For columns, where it depends upon the axial forces, if axial force is of good size, then it is zero point 0.8 of gross moment of inertia, medium, then zero point 0.6, then zero point 0.4. Now eventually this had further reduced, further been uh, changed by the ACI committee, as well as the IS code also. You are seeing that 0.7 Ig and 0.9 Ig are the two values that have been recommended by the codes for modeling the I for the columns, effective I for the columns. Now if we see this moment versus curvature diagram, your yield curvature is nominal moment upon yield moment into the nominal curvature. So this curvature ductility has been shown. So moment curvature relationship is very critical to arrive at the section properties, and as the crack will keep on increasing, you can see that from elastic to inelastic stage, your I will keep on changing. So EI is the stiffness of the beam, that is E into I effective. It will, when you are taking the crack properties and make it I effective, your bending properties of the beam also changes. So the moment capacity of the element reduces based on how much crack has been developed in the section, and from that you can develop the critical capacity of the structure that is used to resist the demand of the earthquake. So for each beam, for each column, for each wall, if you capture the element behavior in moment, in flexure shear, you will be able to categorize, you will be able to understand better how the building will going to resist the earthquake forces. So initial hypothesis of stiffness, which is independent of strength, is wrong. So what we can say is that uh, stiffness is independent of strength. So stiffness has to be dependent on the strength as well. Okay. So that is what is the derivation given by Nigel Priestley. And if you see in one of the graphs, it is shown that one is a linear graph, okay, which is a linear curve. If you take moment curvature relationship, okay, in that case, your y value keeps on changing. But as compared to that, phi y is always constant for one element. For moment 1, moment 2, moment 3, it will not keep on changing. Okay, so if you find out the stiffness, the slope of this curve, okay, the stiffness has to be different. It cannot be a same stiffness for all the moments that are going to act on the beam. So in one case, it will act give higher capacity, in one moment it will give lower capacity for the same reinforcement and section size. Okay, so stiffness keeps on changing based on the force applied. So that is relevant from the two graphs that are visible. 5i is constant. Your initial line is keep on shifting downwards from M1, M2 to M3. So this shows that stiffness is not independent of the strength. So these values are given in ACI 318 for columns 0.7 of I gross, walls that are cracked 0.7, uncracked it is 0.35, and for beams it is 0.35 of I gross, flat slab 0.25 of I gross. So you can also understand this more by referring to the initial document that was written by Wong and Sommer. Okay, so this can be downloaded and can be referred for this understanding of the section properties. So conclusion, EI is directly proportional to strength, okay, and which is axial force and the steel ratio. And if you refer to this uncracked section, green shown by the green line, and cracked section shown by the violet line, there is a difference in the stiffness of the element. Okay, and correspondingly, as you will see that the yield displacement value changes. Based on that, your ductility also changes, and in that case, the ultimate displacement is also changing for the elastic design. Okay, so if you draw a horizontal line, okay, that is a red line, you will see that the stiffness of the first curve with the green is higher, stiffness of the second curve with violet is lower, and the total displacement also changes. Your ductility value also will change accordingly. And you can see this violet horizontal dotted line, your P design, that is the design base shear, reduces drastically. The change in the uh, design shear force for the building reduces. So it will be able to take less of the shear force and higher of the displacement. That is what we can see from this graph, that VEC upon cracked upon R, VE gross upon R. So VE gross is the higher capacity, VE cracked is the lower capacity. So your design base shear changes and your ultimate displacement changes, curvature ductility changes, time period of the building changes by using the crack section properties. So it is not possible to perform a precise analysis of the elastic structural periods or elastic distribution of the required strength through the structure until final strength of the elements has been determined. This means conventional seismic design based on elastic stiffness of the element and considerations based in the force must be an iterative process where stiffness of the elements are changed in each iteration. However, this we are not following, but we have normalized this statement by reducing our effort to a single value of single stiffness modifier for all the columns, for all the beams, for all the slabs. We are using the same 0.7 or 0.25 or 0.35 of IG. We are not giving different gross effective stiffness modifiers based on the force, based on the behavior. Okay, so we are giving the same stiffness modifiers to all elements of the types mentioned in that table. So thank you guys for listening. and if you have any queries in its application, you can do that. But what you can do, you create a model with gross modifiers, that is the case 1, and create a second model with effective section modifiers, and uh, design for both cases, in which one is ultimate and one is the effective section modifiers. And for all ultimate load cases, you should consider the crack properties, and for the analysis, you should consider crack properties only for the earthquakes. Okay. Or so once you give in the analytical model, it will be relevant for all. The full model will consider crack sections in the analysis and crack sections in the design. Now in wind, if your structure is not going into the non-linear range, and if you are giving the crack section properties, okay, in the wind case, in analysis, then in that case your displacement will be higher for wind. However, once you will design for it, your ultimate action is going to crack the structure. So basically, cracked section properties will help you to capture the higher displacement as well as the cracks during the ultimate load cases. So that is the basic agenda, so that you capture the exact reinforcement requirement as well as the time period of the building for using the section modifiers for the ultimate load case as well as the serviceability load cases. So remember that correct modifiers are used for ultimate load case, and your this for serviceability load case, the different set of modifiers has been given. And for the response spectrum, we have to use unscaled response spectrum for checking the displacement in the seismic uh, cases. So thank you again for hearing, and give your feedback and any queries you have towards understanding of the effective section modifiers. Yeah, thank you. Bye.